This is Chapter 1, Section 1, Chemistry Notes. Chemistry is the study of the composition, structure, and properties of matter, the processes that matter undergoes, and the energy changes that accompany these processes. We have 6 different types of chemistry. The first type is organic chemistry. This is studying anything that contains carbon. Um, Objects that contain carbon are objects that are currently alive or have ever been alive. Inorganic chemistry, the study of non-organic compounds. So this is everything else on the periodic table. Most inorganic chemists pick a specialty area. So maybe they pick sulfur, and so they spend most of their research time studying things that are based off of sulfur. Physical chemistry is the study of the properties and changes of matter and the relation to energy. So anytime in here it talks about energy, generally it's referring to heat. So they'll study chemical reactions and determine how much heat is given off or how much heat is taken in. Analytical chemistry is the identification of the components and composition of materials. So think analytical, analyze. Biochemistry, the study of substances and processes occurring in living things. Remember the prefix bio means living. And lastly, theoretical chemistry, the use of mathematics and computers to understand the principles behind observed chemical behavior and to design and predict the properties of new compounds. So most theoretical chemists work with ideas rather than actual objects. Chemical substances have definite composition. So the definite composition is generally shown to us in a chemical formula. So sucrose, which is table sugar, the formula for it is C6H12O22. Water is H2O, carbon dioxide, CO2. So if you can give it a chemical formula, then it is considered a chemical substance. We have 2 different types of research. The first type is basic research. This is just to gain knowledge. If you like to study a certain area of chemistry, you're studying it just for yourself. The second type of research is applied research, and this is trying to solve a problem. One way that chemistry helps society is through technological development, and we see lots of this in the examples they give: computers, catalytic converters in cars. This reduces pollution. Biodegradable materials. There are potato chip companies now that produce potato chip bags that will biodegrade in the ground within 30 days. So even though we don't consider a potato chip bag technology, it is a technological development. All right, that was all of Section 1. Now it is Chapter 1, Section 2 notes. Volume is the amount of three-dimensional space an object occupies. Units that we typically use for volume are milliliters. Sometimes you'll also see it as cubic centimeters. So the abbreviation for that is cm to the third power. But generally in our lab and in our class we will use milliliters. Mass is the measure of the amount of matter. And matter is anything that has mass and takes up space. These are the same definitions you've always known. The basing building block of matter is the atom. It is the smallest unit of the element. It has to contain that element's identity. We know that there are things smaller than atoms, but when we look at subatomic particles such as protons, neutrons, and electrons, they no longer have the same identity and same properties of any particular element. So this is why we consider an atom the smallest unit. An element is a pure substance that cannot be broken down into simpler, stable substances and is made of one type of atom. A compound is a substance that can be broken down into simple, stable substances. Going back to an element, atoms of any particular element are the same no matter where they come from. So if you find gold in China, it will have the exact same composition as gold that's found in Africa. Chemically, they're the exact same thing. Same thing with compounds. If you go to a salt mine in Asia, the salt NaCl is going to be exactly the same as the NaCl that they find in salt mines in Utah. They will have the exact same composition. All right, we have two different properties. We have extensive properties. This depends on the amount of matter that is present. So volume, mass, the amount of energy in a substance. Extensive properties will generally have some kind of number involved. So 1 gallon of water, 1 cup of water. It doesn't matter how much you have, it's still water. And then we have intensive properties. It doesn't matter how much you have. So melting point, boiling point, density. Um, the boiling point of water is 100 degrees Celsius. It doesn't matter if we have a gallon of water, a cup of water, it's still 100 degrees Celsius. So extensive depends on the amount. It will have an exact number. Intensive doesn't matter how much we have. Physical properties and physical change. A physical property is a characteristic that can be observed or measured without changing the identity of the substance. If we melt water, it's still H2O. If we boil water and it makes steam, it's still H2O. Phase changes are all physical properties. So we're talking melting, boiling, and freezing. These are all physical properties. A physical change is a change in a substance that does not involve a change in the identity of the substance. Grinding, cutting, melting, boiling. It's all physical. If I take a piece of paper and I cut it up, it's still paper. When you clip your fingernails, they're still fingernails. All of these are considered physical changes. Right, so phase changes, this is just going from solid, liquid, gas to plasma. These are all physical changes. In the solid state, matter has definite volume and definite shape. In the liquid state, matter has definite volume but an indefinite shape, so we know liquids will take the shape of their container. Gases, matter has neither definite volume nor definite shape. Plasma, high temperature physical state of matter in which atoms lose most of their electrons. Plasma is usually found in stars, sun, lightning, those different things. Oh, there's some more examples of plasma. Chemical property relates to a substance's ability to undergo changes that transform it into different substances. A change in which one or more substances are converted into different substances is called a chemical change or a chemical reaction. So in a chemical change, we are now making something new. An example would be burning. If I burn a piece of paper, it's no longer paper. Now it's ash. We show a chemical change by writing a reaction. So in a reaction, we have reactants. These are what we start out with, the beginning items of our chemical change. And then we have our products, and these are the things that are being formed. This is what we end up with. We separate the reactants and the products with an arrow that is also called a yield sign. Here are some evidences of a chemical change. Bubbles. When you see bubbles, that generally means that a gas is being released. Um, Make sure that when you refer to bubbles that you're not talking about boiling, because boiling is a change of state, not a chemical change. So if you see something forming bubbles without any heat added, it's releasing a gas, so it is a chemical change. A color change. This is generally considered a chemical change. The formation of a precipitate. A precipitate is when we form a solid from two liquid substances. It's generally a very soft solid, so it's generally a powder. But if you take two liquids and pour them together and a solid settles down in the bottom, you've formed a precipitate. This is a chemical change. And then the release of energy. And generally, energy is considered heat or light. Going back to this slide, electrolysis of water. When you boil water and become steam, it is still H2O. When you electrocute water, so when you send an electrical current through water, it is separating into hydrogen and oxygen molecules. Boiling is just a change of state. It is a physical change. Electrolysis, or electrocuting water, is a chemical change. We are now creating hydrogen gas and oxygen gas. It's important to remember that. Energy is always involved when physical or chemical changes occur. Generally, when we talk about energy, most of the time we're going to talk about heat. There are a couple of instances where we'll see energy being produced as light. Energy can be absorbed or released in a change. It is not destroyed or created. This is called the law of conservation of energy. This is a flow chart that you can use to determine what type of matter you have. So you can take in substance and answer these questions about it and break it down into homogeneous mixtures, heterogeneous mixtures, compounds, or elements. A mixture is a blend of two or more kinds of matter, each of which retain its own identity and properties. These are things that can be physically mixed together, so like sand and water. They can be separated. So to separate sand and water, I would use filter paper. The sand will stay on top of the filter, the water would drip through. Homogeneous mixtures are called solutions. They are uniform in composition, so remember homo means same. This means that the substance will look exactly the same all the way throughout. Heterogeneous mixtures are not uniform throughout, so you can see distinct layers or distinct parts of the mixture. Pure substances have a fixed composition, so this is generally an element or a compound. If we change its composition, we have now changed that substance. Pure substances are going to be different from mixtures. Pure substances are exactly the same no matter where they come from, and they have the exact same properties. Mixtures will vary. An example, salt will always be NaCl. This is regular table salt. It will always be the same no matter where you get it from. It always has the same properties. Mixture, so Italian dressing. No matter which restaurant you go to, their Italian dressing is going to be a little bit different. They might all contain oil and vinegar, but they don't contain it in the same amounts or the same ratios. Here are some examples of homogeneous and heterogeneous mixtures if you're having a hard time figuring any out. All right, and on to Chapter 1, Section 3. This is an introduction to the periodic table. If you'll notice, some of the elements on the periodic table, their symbol doesn't match up with their name. Most of these have a Latin name, which is their older name, instead of going by the modern name or the English name that we have given them. This periodic table is broken up into 4 different parts. We have the metals, nonmetals, metalloids, and noble gases. Vertical columns in the periodic table, I generally call these groups. So I might say the carbon group or the nitrogen group. Everything in vertical columns have very similar properties. Everything in group 1 on the periodic table, they're highly reactive with water. Horizontal rows on the periodic table, these are called periods. And we will notice changes across periods on the periodic table. We'll get into this in a later chapter. Metals, an element that is good electrical conductor and a good heat conductor. Most metals are solids at room temperature. We have one metal that is not, that is mercury. Malleable means that they can be rolled into sheets. They're real flexible. Ductile, that means they can be drawn into wire. Metals can also conduct electricity and heat very well. One property of a metal that they didn't show is luster. So this is how shiny a metal is. Nonmetals, an element that is a poor conductor of heat and electricity. Generally, if it's a poor conductor, we call it an insulator. Properties of nonmetals, most of them are gases. If it is a solid, it's going to be very brittle. And when I mean brittle, like a stale cookie. It doesn't just break, it's going to shatter. And these are poor conductors of heat and electricity. Metalloids, an element that has some characteristics of metals and some characteristics of nonmetals. These are all solids at room temperature, and these are called semiconductors. These are found a lot in computers and cell phones. Anything that has a kind of electrical circuit will have a semiconductor. We only want it to conduct small amounts of heat and electricity. And the noble gases, these are in group 18 of the periodic table. These are generally unreactive. They can be forced to react in lab, but you will not find them reactive in nature. All of these are gases at room temperature. That is the end of chapter 1 notes.